Today I'm going to talk about the next lab assignment, which is lab 3. I had it due October 27th, but I forgot about fall break is next week, right? We'll miss a lab session.
Yeah.
So I'll add another week to that. Okay, so because I wanted to have it due in three weeks or so, but I'll add another week to that. Okay, make sense? Yes. Yes, the midterm will be the week after next, and I have some slides about. I have a slide about that. I thought I did. Hold on a second. Quiz. Oh, well, I thought I did. I must not have pushed it up. Yeah, so it'll be the week after next. So it'll cover everything we've covered up so far in class. So basically the programmed I/O interrupts, pulse width modulation, bit manipulation, the I/O protocols that we covered, and system Verilog. Okay? Make sense? So you'll be able to take it on Dropbox anytime during the week from midnight on Friday, midnight on Monday to midnight the following Friday. So this one's just Monday through Friday. You could take it anytime you want. It'll be 75 minutes, one attempt, and multiple choice, like the quizzes. Okay, any questions? And it's open book, open internet. Just don't take it with other students, obviously. And it's I mean, if you do, it's obvious because it says when you opened and closed it on the spreadsheet when you bring it up. So yeah, don't take it with other students. You're not supposed to communicate with anyone when you're taking it. Okay. Okay. So we had a quiz last week on Dropbox, quiz 5. I think this is the right one, right? Consider the Verilog module shown below. How many input signals are specified? That would be clock, reset, load, and seed, so 4, right? That's easy. Assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 clock cycles after the reset pulse? So when you reset, the state goes to 1, 0, 0. And this is the right quiz, right? You guys took this one last week? Okay, just making sure. So what's the value of state in the first 3 cycles? So I think this one do I have a table? Yeah. So state starts out as 1, 0, 0 in cycle 0, because that's what we reset it to. And then the idea is that you calculate the next state in this always block, and then the next state will take effect the next cycle. All right, so next state 2 will be just 0. Next state 1 will be whatever state 2 was. Okay, so state 2 was 1, right? So that 1 gets transferred over here. So the previous value of state bit 2 gets put into the next state bit 1. And then next state 0 is going to be state 1, the old state 1 or the old state 2. Oh, sorry, the old state 1 or the old state 0. So you take the 2 low order bits here, 0 or 0, right? And that's 0. So then you transfer this value, 0, 1, 0, down to the state in cycle 1. And then you just repeat that. So state 2 is 0, state 1 is going to be another 0 because, you know, it's copied from state 2. And then state 0 is going to be a 1 because 1 or 0. You see that? And then, so you transfer that value down, 0, 0, 1 becomes the current state. And then state 2 is 0, state 1 is 0, and state 0 is going to be 1, which is 1 or 0 or 1, right? And actually that state will just sort of settle at 0, 0, 1 indefinitely until you reset it again. Okay, give the value of signal A in the first 3 clock cycles. So I have another table here. It's similar, except in this case, This one's a little confusing because I start out by assigning A to 101, and then the next state logic has a combination of a blocking and a non-blocking assignment. So this blocking assignment actually will be, the value assigned to this A in this blocking assignment will be effectively substituted down into the line below, right? So what this is saying is I'm going to shift A one bit to the left, and then I'm going to XOR it with 111. So basically shift it one bit to the left, and then if you XOR by 111, you're just flipping all the bits, right? That's a, basically a complement operation. So basically you take 101, you shift it one bit to the left, which will make it 010, right? And then you flip it, which makes it 101 again. So what ends up happening here is that it'll just be, I call it A, this A intermediate value is the value after this first line of code. But what'll happen is that state will just stay at 101. It'll just get stuck there. Okay? And what is the problem with the following code? This one has an issue because it's a combinational logic behavior, right, for this always statement. But it's not combinational because it has a loop in it, right? Because you assign A and then you use A, right? So if you actually built this, it would create an oscillator. A would be changing as fast as the logic would permit it to, right? In whatever technology you're building this into. But in Verilog, you'd get an error because you explicitly say it's supposed to be combinational, so the compiler would give you an error there. I've never tried to do this on an FPGA. I don't think. I have done, no, I have done something like that. A long time ago, I tried something like that. I tried to do asynchronous logic, asynchronous logic on an FPGA, basically a clockless state machine, which works kind of like that. Although you're supposed to design it to be stable, but it's hard to actually achieve stability. But anyway, yeah, you can't. That's the problem there. It's got to loop back. Okay, what are the first three values of A generated from the snippet below? So another similar one. So this one resets with A 10101 and cycle 0. And then the next A is going to be this bit manipulation. So you start out with A bit 0, which is 1. And then you're going to concatenate that with 2 copies of A bit 1, right? Which is 0, so 0, 0. And then a complement of bit A3, which over here bit A3 is 0, so that'll be a 1. And then A bit 2 XOR A bit 4. So we're looking at 2 and 4, so 1 XOR 1 is 0. That makes sense? So this is the same kind of question, it's just using the bit manipulation operators. I'll just skip over the next 2 states unless anyone has a question. Okay, everyone okay with that? Great. Okay, so the next topic is we want to cover one more bus protocol, and that's the Avalon bus. So when you guys took 313 and also when you did the previous lab in this class, you used Platform Designer and you dropped a bunch of modules into this system on chip that's comprised of IP blocks, which are basically Verilog designs that Intel is providing to you, like an IP library. And then, you can make connections on those, and then they can communicate over standard protocol. Or there's actually more than one. You can choose AXI or Avalon. But you never really looked at how those connections were made. So we're going to take a closer look at that so we can build our own IP blocks for the platform designer. So the Avalon protocol is a master-slave. So it's like SPI, and it's synchronous. So there's a clock involved. But the main difference from there's two big differences from, like, for example, SPI. The first is that this is a parallel bus. So instead of sending 1 bit at a time, you send all the bits that form whatever the bus width is. So like you can have a 32-bit bus or 64. I think the maximum is 512 or maybe even 1024 bits wide. And so because it's a parallel bus, it's a higher performance bus than SPI or I2C. It's much faster. And it's designed for, it's designed for basically an on-chip network, network on chip, or a system on chip interconnect. The other difference is that with SPI and I2C and with JTAG, you had a master and connected to the slave, and the wires were actually connected directly. So the channel was formed of wires that were directly connected between the endpoints. But in Avalon and in AXI, that's not the case. They have this thing called a bus module that actually goes between. So the master basically is sending signals out to the bus module, and then the bus module is doing something to those signals before it goes out to the slave. Right? So there's not a direct connection. The master, they both are communicating, both ends of the bus are communicating not with each other directly, but through the Avalon bus module that acts as an intermediary. Does that make sense? So there's not straight wires connected from endpoints. They go through this guy middleman, basically. So the reason for that is because, if you guys remember from when we talked about programmed I/O, the master is able to talk to multiple slaves through the address. So you send an address out, and then that address is read by the bus module, and the bus module has a knowledge of the address mapping. So when you go into Platform Designer, there's that tab that has the address mapping. That address mapping is encoded in the bus module. Right? So that's the way that, and I don't know exactly how it works. I guess there's a table or something in there. So like if I want to write to address 10, that my request is registered with the bus module, and the bus module's job is to figure out which endpoint, which peripheral it corresponds to address 10, and then it will forward my request out to that, right? So now it's a little confusing though, because if you look at the signals that make up for example, the master port and the slave port, a lot of the names are the same. So if you look at the list of signals, you're like, oh, they both have something called address, so that address is probably connected. No, it's not. The address, even though they have the same name, it's not the same signal, because all these signals go through the bus module. Okay. Now the other thing is, you'll notice there's a lot of signals here listed. It's a little overwhelming, but not all these signals are required. Most of these are optional. It depends on what you want to do. You could you could include or not include certain features in the channel, and then you end up with just a subset of these guys, right? So there's a clock. So this is from the master side. So in our case, usually the only two masters are the CPU or a DMA controller. A DMA, remember I mentioned DMA briefly at the beginning of the semester. DMA is where you have this thing where it will take care of moving data on behalf of the CPU. So whenever you do a high-speed transfer of data, like for example between your hard drive and memory, or between memory and the video card, or even between memory and your Ethernet, that is not, the CPU doesn't get involved in that directly. It's handled by this DMA controller. The DMA controller is a data mover, right? And so generally the DMA controller will have master ports that will take care of that. The CPU could do data movement. You can copy blocks of data with the CPU with programmed I/O, but it's slow. And today I'm actually going to show you why it's slow. I'm going to walk through a demo that will actually illustrate why the CPU is slow when it does programmed I/O. Programmed I/O is not designed for high-speed transfer of data. It's only designed for control and status registers. Okay, so let's see. Let's take a look at those signals. So the master interface has clock and reset as usual. There's an address, which can be 1 to 32 bits. Now, generally, the address width on the master is going to be wide because it has to cover the whole address space. But when you have a slave port, its address because it's not the same, it's not directly connected to the master's address, it'll be shorter. It only has to cover its own address space. So if I'm a peripheral and I have a slave port and I have, say, 16 kilobytes of addressable, addresses under me, I only need to have an address that would cover 16 kilobytes, the log base 2 of 16 kilobytes, right, which is 14 bits, right? So, so that's the address. The address is, by the way, the address is byte, always byte addressed. Then there's a byte enable, and the byte enable is used because it's a parallel bus. So the width of the bus, the data on the bus can be, this is showing 816. I guess it only goes up to 32. I'm thinking of AXE can go up to 512. I guess Avalon only goes up to 32. I'm kind of surprised about that. But the data width of the bus can be set. But if it's more than 8, if it's more than 8 bits, then you have a problem if you only want to send 8 bits, right? So if I have a 32-bit data bus and only want to send 8 bits, you would need to have this byte enable that would allow you to basically tell the slave, look, I'm sending 32 bits because I have to, because it's a parallel bus, but only the low order 8 bits represent the data I want to send you. I don't want to send you all 32 bits, right? So that's what the byte enable is. It's just, it can be, they're saying the width can be 2. So if it's a 16-bit bus, you'd want the byte enable to be 2 bits, and if it's a 32-bit bus, you'd want the byte enable to be 4 bits, because the byte enable would be 1 bit per byte in the bus, right? 1 bit corresponding to each byte. And then there's a write control signal. There's a read. Where's read? Yeah, read and write are 2 separate signals, 1 bit wide. It just tells it what you want to do. Then there's read data and write data are both separate. So it's full duplex. You've got data going both directions. Then there's something called wait request, which I'll talk about in a minute. There's an IRQ. There's an IRQ number, end of packet, read data valid, and flush. So most of these guys on this second column I've never used. I mean, obviously the IRQ is an IRQ. The flush is used for read transfers where the master could tell the bus controller to flush any pending reads, right? So this signal, the reason I've got a box around it is because this is the one signal that is only on the master. You won't see this on the slave side because this is intended only for the master to talk to the bus controller, not to the actual slave. The slave doesn't see the flush signal, right? And then end of packet is for streaming transfers. Remember, we talked about with SPI, we can do streaming mode. In fact, you guys did that with Lab 1. Avalon is a similar thing. We're not going to worry about it in this class, though. And then wait request is the only one we want to talk about. So wait request is used for the slave to indicate to the bus controller, or the bus module, I should say, that it needs more time to complete the read. Okay, so by default, the Avalon reads are assumed to be a 1 cycle latency. So it's going to take, if I send you an address, I'm expecting the data back in the next cycle. But if the slave isn't that fast, it can't provide the data in 1 cycle, then it can issue this wait request. Okay, so it's kind of like we talked about in I2C, there's a similar feature called clock dragging? I forget what it's called now. What is it? But basically, in I2C, the slave can hold the clock down, the I2C clock, and that would gives it more time to be able to respond to the read. I can't remember the name of it now. Clock dragging, clock stretching. Yeah, but in this case, the wait request is used for that purpose. Okay, and then on the slave side, you have similar signals. You'll see, read data, write data. There's an address here. Like I mentioned, though, this address will only be as wide as it needs to be to cover however many addressable locations you have in that slave port. And then there's some other stuff over here that we won't be using. Then there's chip select. This chip select, I've got it highlighted because there was no chip select on the master side. The chip select is only from it's only on the slave side because the bus module is what's driving this. So basically, the bus module is going to see a request from a master port. It's going to use the address to figure out which slave it's targeting, and then it's going to use the chip select on that slave to indicate that that's the targeted, that's the slave that it wants to talk to. And then there's a begin transfer and byte enable. Byte enable, actually, that's also on the master. I don't know why I have that highlighted. Begin transfer is the first bus cycle of each new Avalon bus transfer. This one is optional. I don't think you need to have streaming enabled for this, but I've never turned that on, so you don't have to worry about it. Okay, so here's an example timing diagram then for a read. So if we're designing a slave peripheral, which is what we're going to do in lab 3, you're going to sit there and wait for chip select, basically. So chip select is active high. When that goes high, you're going to see an address. Now again, it's not going to be the same address that the master puts out, because the address that you see here on the slave side will be whatever the master put out as the address, but you're going to subtract the base address of this peripheral. So if the base address of this peripheral were, say, 16, right, and the master puts out 20, right, then this address on the slave is going to be 4, because it's going to be 4 bytes into the address space of this guy. Okay, so keep that in mind. This address does not include the base address of the peripheral, because the base address can change. You guys can set that to whatever you want the base address to be inside of Platform Designer. And then the read signal is active low. So there is an underscore n here. So the read is low here, indicating a read, logic 0. And so basically the expectation with Avalon, it's nice and simple, is the address comes in one cycle, and the slave is expected to put the read data out on the next cycle. Right, that's basically, that's it. Makes sense, right? Now, if it takes more than one, if the slave needs more time than one cycle, then it can use the wait request. So if it needs more time, it just basically within one cycle of the slave seeing the chip enable, the chip select high and the read underscore n low, right? Within one cycle of that, it needs to assert the wait request. And then it can hold that wait request as long as it wants. But when it's ready to respond, it drops the wait request, and in the cycle following that is when it's expected to provide the read data back to the bus controller, or the bus module, right? So read on the next rising edge after wait request deassert. So wait request deasserts here, and it's the next rising edge that you're expected to sample that read data, right? Or the bus module is going to sample it on the next rising edge. That makes sense? Okay, so then on a write works the same way, except there's no data coming back with a write. So there's a write underscore n and a chip select. So in this case, the slave will see at some point the chip select will be high, write underscore n is low, and then there'll be an address and write data that will both be asserted at the same time. And it's expected to write on the first rising edge where those signals are configured that way, right? And there's no acknowledgement with Avalon. AXI, you might have heard of AXI. That's the protocol that you've got, like, for example, in your phone. That one is a more complex protocol, and that one does have an acknowledgement, even for writes. But there's no acknowledgement for writes on Avalon, which is why, I don't know if you guys noticed this, but like when you program the Neos processor from the machines here, it sends all the data into, it writes all the data, through the JTAG, and then it has to read it all back to confirm that the write actually happened, right? So just because there's no acknowledgement there. And then write also has the wait request, so you can also drag out writes if you want from the slave side by using the wait request. Okay, and then from the master side, it's similar idea, except in the master side, obviously the address is an output instead of an input. So on the slave side, the address is an input. Read underscore n is an output instead of an input as it was on slave. But in the wait request is an input. So you can see that it's the master's responsibility to honor the wait request that comes back from the slave on a write or a read. But you guys don't have to worry about that because we're using the CPU for the master side. So you don't have to implement the master interface. You only have to implement the slave interface if you're designing a peripheral. Okay. Okay. And so I just show the write and read for master or for master side. Any questions about that? Okay. All right. So in the next lab, we're going to, I've got the lab posted here. So this one's pretty simple. We want to do pulse width modulation again with the LEDs, except this time we want to implement pulse width modulation in hardware. Have any of you noticed some weird flickering with lab 2? So the PWM doesn't work well in software. I don't fully understand why. I mean, aside from the obvious, which is that the software is behaving non-deterministically. You know, you don't know what the timing is of the instructions being executed necessarily, because if you have a cache miss or an interrupt or something like that, the CPU may temporarily stop executing your code, right? So, and the software may not be able to keep up with the PWM signal. So if you crank up your PWM frequency, you know, maybe the software isn't fast enough to keep up with it, but we don't have any way to know that, right, in our code at the moment. I mean, I guess you could probably build some checks in, but right now you just have to hope that the CPU can keep up with the schedule, the PWM schedule for whatever frequency you specify, right? PWM is typically not done in software for that reason. It's usually done in hardware. But for whatever reason, as I mentioned at the beginning of the semester, Intel doesn't provide a PWM module in the platform designer. So we're going to make one. And so we want to make a module called LED PWM, and it'll control the brightness of all 26 LEDs. But this time we want to make them separate. We want to make them all individually controlled. So the idea would be to have a module that you can write a word to it, and that word will contain a bit mask. So the word that you write to the module will have a 26-bit value. Of course, it'll be 32 bits in reality, but 26 of those bits will correspond to each of the 26 bits LEDs. And then for each 1 bit in that value, we're going to tell the module to light that LED up to full brightness. And then we'll have the hardware dim it down from full brightness to 0 in 1.3 seconds, 1.3422 seconds to be exact. So the idea would be that we'll have a counter, a 26-bit counter, which will just get refreshed to all ones whenever you light up an LED, and then it will just decrement once per cycle after that. And so 26 bits decremented, what's 2 to the 26th power? It's like 32 million, right? Sorry, 64 million. Sorry, 64 million, right? And if you decrement a 64 million count at 50 million counts per second, once per clock cycle, it takes, 1.3 seconds to go from full to 0. And then you can just use that value as your duty cycle, right? Does it make sense? Not the whole value, you may just have to use the upper bits of it, but basically that will represent your duty cycle, right? So the CPU then will be able to hit individual LEDs, and every time it hits one of those LEDs, it'll go bright and then dim, right? And so the software will control that process, which LED it wants to bring up, but then the hardware will control the PWM as well as the, the dimming, right? So if it works, and we want to be able to set a random LED every 90 milliseconds, or 50 milliseconds or 70 milliseconds, depending on what mode you have it in. So if everything works, it should, I have a little video here somewhere that shows what it looks like when it's working. Yeah. Yeah, there should be a link.
Right there, the correct operator.
Oh, right here. Yep, thank you. Yeah, there's a link here. That's a little whoop. Oh, that's crazy. Stop. Okay. That's not playing on the projector. It's just playing on my, yeah, some crazy video setting. But anyway, you'll see. You can click on it in the lab description. So basically, the lights will come on and then dim out. It looks kind of like Christmas lights, basically, that light up and then dim. Make sense? Okay. So the next question is, how do we create one of those modules? You guys know Verilog now, and you can write a sequential logic in Verilog that can talk to Avalon now, right? So now, but the problem is, how do we actually get it into the platform designer? So I'm going to do a quick demo of how to set that up. It's actually fairly easy. So I've got so I've got Quartus pulled up here, and currently I've got no LEDs. I don't have an LED on this one. This just has the basically just an SDRAM controller and clock reset. Okay. So go into a platform designer. This guy plugged in too. Should have a system here ready to go. Neo system. All right, so I've got this system set up, and this is just a basic thing. Now this actually does have an LED's output, but I don't have it connected. Okay, so if you want to create a new component, you just go up here to New Component. Just double-click that. Oh, not that one. It's one I already made. Okay, so then you give it a name. So we'll call it. Now, in this case, I don't want to do the LEDs thing. I'd like to time. So I'm kind of curious how fast. I always say that programmed I/O is slow. Right? Programmed I/O is not a great way to transfer bulk data. It's only designed for controlling peripherals. It's not designed for copying data. But how fast would it be if you copied data? Like how fast? What is the bandwidth or what is the throughput of the Neos processor just hammering as fast as it can, sending data across the Avalon bus? How fast could it do that? Now there's a way you can do in streaming. There is a streaming mode. I actually don't know how to tell the CPU to use the streaming mode. But if we don't use streaming mode, if we just do individual Neos, Avalon transfers, how fast can we do this? How frequently can we do that? Is there a way to measure that? So let's see if we could figure that out. So if you create a component, I'll call it Avalon, I don't know, Avalon tester. It doesn't really matter what it's called. And I'll call it under name and display name, Avalon tester. Avalon tester. Can you guys see that okay in the back? Let me see if I can change the resolution here. View. Is that better? Yeah, that's better. Okay. Okay. Oh yeah, but now the problem is I can't see the buttons at the bottom. There we go. That'll work. Okay, so I'm going to give it a name, and then you go to signals and interfaces. So this is where you define your interfaces. So you just double click on add interface, and the first one you want to add here is the clock input. So we need a clock. I'll just call it clock. It'll be a clock sync. And now this is the part that's confusing, because just because I added that clock didn't actually add the input port. It added a category of input ports, or a category of ports. If you want to add the physical port, then you have to add the signal under it. So you say add signal and say clock, right? So now I have clock here, and under there I have this clock underscore clock. I think I can change the name though, just make it clock. And it's a 1-bit signal, it's an input. I don't know why you have to do that. It seems redundant, but I don't know. And then you want to add a reset input here. And I'll call that reset here. And then again, you have to add the signal reset. And there was a reset IRQ option. Do you see that? Yeah, there's some kind of reset associated with IRQs. I've never used that. Okay, and then I want to add a slave interface for the Avalon slave. So you hit, you go and you can choose between. Now this is pretty neat. Look at all the interfaces they have. They have AXI master, AXI slave, AXI 4 stream, APB. I've never even heard of that one. AHB. I think that's an older bus protocol. They have HSSI bounded clock, high speed serial. I think this is for like if you're doing gigabit serial, like you would need if you're doing like HDMI or like gigabit Ethernet. Interrupt receiver, interrupt sender, tri-state conduit master. Well, we know what the conduits are like when you just, like the LEDs, right? When, like you guys use that for the LEDs, the external thing. Or no, they just have regular conduit too, right? Avalon streaming source. We just want an Avalon memory map slave. So you pick that. Okay, now you get to choose which features you want to use. So if this peripheral is a read-only or a write-only slave, you don't have to add, you don't have to have the read and the write control signal if you can only do one or the other. I'm going to add them both though. So I'm going to add a signal. Well, I want to add address. That's required. And what's the width of the address? Well, this is going to determine how much memory space your slave has. So if you just do one, actually the address isn't required. I'm sorry, I take that back. You don't have to have the address if there's only one word on your peripheral. I'm going to put it in just for the heck of it. I'll put a 10-bit address. That'll give me 1024 bytes. Chip select. Okay, that's an input. Read data. I'm going to make that 32. And write data, I'll make that 32. Okay, and wait request. I'm not going to put wait request because I'm going to assume that this peripheral can always do a read or write in one cycle. Write response valid. I don't remember seeing that one. Lock, byte enable, burst count. All the rest of this stuff is, yeah, I don't need any of that. Okay. Oh, I need a read and write control signal. Read and write. All right. Cool. Now, the problem, notice that this is write. It's not write underscore n. I think this is actually, I think this one's active high. Right? Is it active? Oh, you can switch it to write in. Yeah, you can actually switch it to active low, but there's an option to use an active high version, so that's good, right? We'll just leave it active high. Okay, so I think we're good to go. Interface must have an associated reset. So I have to go back up here and I have to set the reset to the reset. So we're good to go. So I'm going to hit finish on there. Okay, now by the way, the next step for this is to create a HDL wrapper for this thing, right? And the way you do that is you go to Files and you click Create Synthesis File from Signals. However, don't do this right away. There's this strange thing in the code. If I do it now, it's going to call the component new component, which was the original name it had here by default. It won't name it Avalon Tester. And once you do that, there's no way to go back and change that I've ever been able to find. So the only way to avoid that problem is to hit finish here. If you hit finish and then save it, and then you go back into Avalon Tester and, oh, sorry, I forgot I should have said edit, not double click, but right click, edit. And now I'll go into files and I should be able to create a synthesis file from signals, and now it's called Avalon Tester. Now here's the issue here. My language choice is Verilog or VHDL. I can't choose system Verilog, so unfortunately we're going to have to use pure Verilog, and there's some strange things in there, which I'll point out. You'll notice, you can probably already tell, it says input wire instead of input logic. That's one of the things right there that you have to worry about with Verilog. So I'm going to go ahead and just save it if I can. I can get to the save button. Save. All right, and then that's it. I can get out of here. Hit finish, save, and then it's going to refresh the system, and then I can add this module just by double-clicking it. Okay, so it finished there, so I can just double-click, and I don't know if I'm going to be able to do this with this resolution. Double-click Avalon Tester, and there's no options here because I didn't add any. Wait a minute, did it add it? Okay, hold on. Sorry, I'm going to have to bump up the resolution here. View, scale, virtual screen. I got to scale it down again. Okay. All right, so now we've got, I'm going to hit finish, and you can see that it added it down here. Hello. It's glitched, isn't it? Come on, buddy. All right, so I'm going to save. I'm going to exit and go back in. All right. No, don't generate. Okay, so if I exit and I go back to Platform Designer, hopefully I'll be able to, that's not encouraging. Hopefully I'll be able to see the whole design. Yeah, that looks good. Neo system. All right, cool. All right, so if you scroll down, you can see the Avalon Tester now. I've got it. So you can see I've got the clock input, the reset, and the Avalon slave. And so all I got to do now is connect those guys. So clock is connected to, or reset's connected to the system reset. Clock will be sysclock, right? And then slave will be data master, connected to data master, not instruction, data master. Cool. All right, I think we're good. So now I can save. And apparently there's no, let's check the address map here. So you'll see in the address map, the Avalon Tester is 0, starts at address 0 and goes to address FFF, which is 4 times 3, 12 bits, right? I thought I had, I guess when you say, okay, when you, I said 10 bits though on the address width, and it's putting 12 there. So that address must have been a word address. Yeah, I'm sorry. So I was wrong about that. The address on the slave is the word address, not the byte address. Because I said it was 32 bits, which is 4 bytes, and that 4 bytes comprises 2 bits. And so when I said 10-bit address, that was a word address. But from this perspective, it's a 12-bit address. FFF. It goes from 0 to FFF. Okay, so let's go ahead and generate this. And while that's generating, I'm going to go back over here to Quartus. And if you go File, Open, inside of if you go to the root directory of your project, so this is the lights directory, you can see that there's a new file in here, Avalon tester.v. So that's where it put that file that I generated. So all I got to do is modify this Avalon tester. The problem is that when I make changes to this file, it's going to use this file when you generate your design in Platform Designer. But when it generates the design, it's going to make a copy of this file in the NeoSystem HDL directory. Okay, so what that means is anytime I change this, I have to regenerate. That's one. And two, and this is the really bad part, if you have an error in this file and you get a compiler error, and you double-click the error, it's going to bring up the copy, not the original. So double-clicking on an error message for this file, don't trust it. Close that file that opens and go back to the original upstream. Okay? So keep in mind that you're going to have 2 copies of this file. You have one in your the root directory of your project. That's the upstream file. That's the one you want to change. The downstream one's going to get overwritten every time you regenerate. But it's also the one that's going to come up if you double-click an error. Okay? So here's the file. You can see that it's pretty much just a wrapper. So I've got an input clock, input reset, input address, input chip select, output read data, output read data, because that's the read data I'm sending out to the master, input write data that's coming in, and then a read or write signal. These all have really super long names because they're machine generated. And yeah, so the problem is, one of the issues is that this is Verilog, and you'll notice that it says wire here instead of logic. This is important because in Verilog, a signal declared as a wire can only be driven, first of all, there's no logic. You can't use logic. But a signal declared as a wire can only be driven by structural code, like another module's output port, or an assign statement. If, however, you drive the signal with an always statement, you have to declare it as a reg instead of a wire. And if you make that mistake, you'll get an error message when you go to compile. But it's easy to correct it once you get the error message. Now you might be thinking, wait a minute, reg? What does reg mean? Register? No, it doesn't. You would think that, but it doesn't. I don't know what reg means, because remember that an always statement can be used to generate combinational logic, or to define, to specify combinational logic, right? You can say, in fact, you could even say always comb, right, in system Verilog, or in regular Verilog, always at star. But even if you do that, anything you set in there still has to be declared as a reg, even though it's not a register. It's clearly just a combinational logic, right? That also includes, by the way, these signals in the module line. If you have any of these guys, like for example, read data, if read data is set by an always statement, which it is going to be, I'm about to do that, then you have to change that wire to a reg. Okay? Okay, so what do I want to do in here? So I want to, I would like to time how long it takes between Avalon reads and Avalon writes. So then I'm going to have the Neos processor try to write as fast as it can, and I want to see that with the with the Neos processor writing and reading, how many cycles elapse from one read to the next read, or from one write to the next write. Okay, so I'm going to create a little performance counter here. So I'm going to say reg. I'm going to create a 32-bit counter called count. Okay, and then I basically going to have that. I'm going to have always Now I can't do always underscore FF because that's system Verilog. I have to say always at pos edge. And I'm going to say clock because I'm actually going to say, I'm going to rename, I'm going to say wire clock. And then I'm going to say assign clock to be, oh, sorry, it is called clock. Never mind. Never mind. I'm good. I was going to rename it because I assumed that the clock had a long name, but it's not. I fixed that. Okay, so always at pos edge clock, begin, and all right, so I'm going to say count is assigned to count plus 1. So I'm just going to add 1, and I'm going to say, yeah, I'm actually not going to initialize it. I'm going to let count come up as a random value. Actually, it'll come up as 0 when I configure the FPGA, but I'm not going to worry about even initializing that. I'm just going to add 1 to it. And then I'm going to say if I get a read, so if chip select, you know what? I think you can actually get away with not even looking at chip select. I think it's good enough just to look at read or write, but I'm going to look at both just to be sure. So I'm going to say if chip select and read. Okay, so if I get a chip select and read, now it's going to notice that on the rising edge of the clock, right? Then I am going to set the Avalon read data to be the count. Okay? So if I read, from the CPU's perspective, if I read, I'm going to return the count, right? And then I'm going to reset the count. Count equals 32D0. And then end. Okay? So now you might say, wait a second, you just incremented the count. How can you reset it? Remember the way the Verilog works is that only the last thing that you do matters, right? So incrementing it here will actually not happen if I reset it. Only if I don't reset it will this guy get incremented, right? So all I have to do is I can keep reading from this guy, and every time I read it, it's going to report back the number of cycles that happened since the last time I read it, right? Because it resets it every time you read, right? Make sense? Of course, the first time I read it, it's going to be a random number. But the second time I read it, I'll have the number of cycles since the first time I read it, right? Okay, and then I can do the same thing for writing, although I'm not sure how I'm going to measure the write. I'm just going to ignore the writes for right now. Okay, does that make sense? Everyone with me on that? Okay, is that all I need? I think that's all I need. I think that's all I need for now. I'm ignoring reset. I'm ignoring the address. I don't care about the address. So I can write to any address. This thing has, an address can be from 0 to 1023 as a word address, right? But I'm treating that as a don't care at the moment. Now you may not always want to do that, but I'm allowed to do that. I'm just going to ignore it for now. Okay, so I think that's it. So I'm just going to save this, and I'm going to go back to Platform Designer, and I'm going to regenerate. And then I just go to Quartus and recompile. Okay, now from the software perspective, by the way, if I go back to Lights Software and Lights BSP, I'm going to regenerate the BSP here. And hopefully, if I look at the system.h, I'll have an entry for that thing that I just made, a base address entry. Of course, it's 0, but so if I look at system.h, I should have something. What do I call it? Neos Avalon something or other. Avalon JTAG. Avalon tester. There it is. Check it out. Avalon tester base 0. Right? That's the base address. So I can just do an I/O read or I/O write to that, and I can access my peripheral from software. So that's good to know that actually worked. So let's close that and let's go back to Quartus and compile. See if if we had an error in the Avalon tester, then we'd get the error now. But this is where you have to be careful, because like I said, if you get the error and you double click on it, it's going to bring up the wrong version of that file. Oh, and I already know I'm going to get an error. I know I'm going to get an error because I forgot. So I'm changing Avalon slave read data in and always, but I forgot to change that to a reg. So that's the error it's going to give me. But I'll show you what the error will say. Something about can't set a structural net expression from an always or something. While that's going, let me just double click the board. Do I have a board? LS USB. Yep. Can I talk to the board? JTAG config. Uh-oh. Am I getting the same issue, aren't I? Kill all. JTAG D. JTAG. So I have not updated. Okay, they were good. Yeah. Yeah, I haven't updated my JTAG D like we did in the lab. Everyone okay with the JTAG stuff now? Okay. Yeah, strangely, I have the same version. What do I have here? Etsy issue. I have Ubuntu 20. I guess we have Ubuntu 20 on these machines. That's probably the issue. All right, so did it finish? Yep, I got an error message somewhere. Yeah, here we go. There it is. Verilog HDL procedural assignment error at Avalon tester line 32. Object Avalon slave read data on left hand of an assignment must have a variable data type. That's what reg is. It's a variable data type. So I can just change that to reg and recompile. Oh, see, I screwed up. Is that the right one? If I double click on it, I get another Avalon tester. See, this is the wrong one. See, I didn't double click it because I already had it open. So if you double click it and you get this one, that's wrong. That one's right. You might say, well, how do you know? It doesn't have the path. The editor doesn't show you the path of the file that you have open. Yeah, it doesn't, which really, I think you have to go to like file properties to get it. Maybe not. Oh, file properties. Yeah, see, if I go to file properties, look, it's in this submodules directory. You see that? See, it's in Neo system, it's in lights, database, IP, Neo system submodules. That's the downstream version. So that's a copy. So I can't close that. I changed it in this one, which is in the root directory, so I should be good. However, do I have to regenerate it in Platform Designer? I don't remember if you have to do that or not. I think I might have to do that, but let's find out. So I'm going to recompile it. I can't remember if you have to regenerate it to make the copy. Oh, one other thing I want to show you. If you go to the edited, if I go to Avalon tester and I say edit, I don't know if it showed this before, but if you go to signals and you click on the Avalon slave and you scroll down, oh, maybe not. Maybe it's over here. Yeah, there it is. Oh yeah, by the way, sorry, one thing I want to clarify here. The see how it says address units words? That's why I gave it a 10-bit address in here and it was a 12-bit address, right? Because of this. You can actually change it to byte address here if you want. In which case, if I change this to byte address, then I think probably it'll be a 10-bit address in the address editor. I'm just going to leave this as word address. But what that means is when you send the address out from the CPU, it's going to divide that address by 4 before it comes to the address lines on your peripheral, right? Because it's set up for word addressing. But in my case, it doesn't matter because I'm not even looking at the address. So there's a bunch of settings in here, but this is the cool thing. It actually is showing you. It's going to show you the read and write waveforms. So based on how you configured the port. So depending on what signals you chose when you set it up, in this case, it's showing me read and write because I added the write pin. But if I didn't have the write pin in there, then it would only be showing me the read side. So you can see how it's showing you how your code is expected to behave in response to a read or write. Okay, so back to Quartus. Is it done? Yep, looks like it's getting there. So I guess you don't have to regenerate after you change it, which actually is kind of confusing because I don't know at what point it copies. I guess it must copy that file from your project directory into the submodules directory when you compile in Quartus, as opposed to generate in SOPC Builder. So that's good because it would take more time to have to regenerate it every time you make a change. Okay, so now the question though is, you might be wondering, like, how do we debug this thing? Like, it's compiling, sure, but how do we know it's going to work? And if it doesn't work, what's going to happen? Well, the board just won't work. So then what do? What's the next step after that? How do you go about fixing behavioral issues with the design if it doesn't work? Well, that's the big question. Presumably, there is a way to simulate the whole system. I have never gotten that to work because you have to generate a simulation model for the Neos processor and the Avalon bus module and everything in the Avalon system and then run it in ModelSim like we did in 6.11. I have never gotten that to work. I've tried to do it, and ModelSim always says that it can't read the model files that this thing generates. So another way to go about doing it is to use signal tap, to just use JTAG to debug on the board, right? So now that this is compiled, I'm going to go over here to Tools, Signal Tap Logic Analyzer. And I already have a bunch of stuff in here, sorry. I already have a bunch of stuff from last time I did. Okay, I'm going to delete that. Okay, so when you start out in Signal Tap, this thing is blank, right? So the first thing you have to do is you have to specify the clock that you're going to use for sampling the data in Signal Tap. So you want to use clock 50. You just type it in, clock_50, right? And then you have to add nodes that you want to look at. So you can say add nodes. Nodes are just signals that you want to measure. And so you get this node finder. Okay, and you want to select, over here you want to look at pre-synthesis. Why pre-synthesis? Because if you look at post-synthesis, it's really confusing to find signals because post-synthesis it'll optimize some signals out, and also every signal you have in your design has multiple names depending on what level of the hierarchy it's in. So if it's in this level, it'll have one name. If it's in that level, it'll have another name. The post-synthesis version only retains one name for each signal. So it's hard to locate signals because, for example, clock_50 is called clock_50 in lights.sv, but it's just called clock once you start drilling down, but it's the same signal. So, but if you go to pre-synthesis, it retains all the original signal names. So it says, you see where it says name star there? You can just hit list. And it'll list all the signals in your design, but it does it hierarchically. So it's not too hard to find what you're looking for there. I don't know why. Okay, there we go. So if I drill down in a Neos system, which is U0, apparently I called it U0 inside of lights.sv. Then you drill into Avalon tester. Then now I'm inside Avalon tester and I can see all the things I've got in there. So I've got chip select, so I'm going to add that. Read, I'm going to add that. And then read data. All the bits are separated. Oh, actually, I can just use that one. They're all together. Write data, slave address, clock, reset, and count. Actually, clock, I don't need clock because I can't look at the clock anyway. Okay. All right, so I've got all those things added. I'm going to hit insert. Notice that only the read address is broken out like that, not the write address. Why? I'm sorry, not address, data, sorry. Read data is out there, right? It's because write data I don't use write data, so it optimized that out. It's still here, though, in terms of the pre-synthesis, because if I attach a probe to it, it's not going to optimize it out because I'll have a probe. But right now, nothing's attached to that bus. All right, so I'll hit insert. I got insert, so here's all the signals here. And so you want to save. And then once you save it, it'll ask you if you want to, I already did this, so it didn't ask me, but when you save it in SignalTap, it'll ask you if you want to add the SignalTap file to your project. You have to do that because what that does is tells Quartus to attach probes to these signals when you compile, and obviously you have to recompile it. So I've got that in there. Once you add that, you'll see the file in Quartus. Actually, it's not there. Oh, because okay, hold on. Let me, I think I have to manually add it because I had it in there and I deleted it so I could do this demo and start out fresh. So I'm going to go to Assignments, Settings, Files over here. I'm going to say, I'm going to add, oh no, where is it? I have to say all files probably, right? Yeah. stp.stp1.stp, that's it. So it should be in there. Cool. All right. I have to recompile now. Make sure I save SignalTap. And recompile again. You can also compile from, hold on, I'm going to stop. You can also recompile from SignalTap. So I'm going to just hit go here. If that works. No? Go away. Go. Now, usually you can compile from SignalTap with the go button there. Okay, so that's compiling. And then you have to add the hardware. You have to tell it that I'm connected to the USB blaster. And then you have to specify the soft file here. So this starts out blank. You just have to point it to that. And if you forget, it'll tell you that you forgot to set up the soft file. And yeah, we should be good to go. I have to wait for it to compile though. So every time you add probes to SignalTap, you have to recompile. So while that's doing that, I'm going to go over here and I'm going to connect to, I'm going to go to the software directory and lights and do a make. And it says I have to regenerate the BSP. So I'm going to just say create this BSP again. I think there's a better way to do this. Instead of remaking it, I think you can just tell it to update, but I can't remember the command for that. I believe it's in the slides though. Okay, then I can go back to lights and make. There we go. Okay, cool. All right, so that software is ready to go. I didn't actually put a software in to actually do anything with that peripheral yet because I'm going to use the debugger to do it instead of the actual writing code. All right, come on, buddy. I got 5 minutes. Go. So once this gets done, I am going to set in SignalTap, you have to set a trigger condition. So you can tell it when you want to see, what moment in time you want it to have it show the signal, the signals that it captured. So I'm going to trigger on the rising edge of read, right? Because the read, remember I used the one that was active high, right? So read's going to be low, and when I read from the peripheral, it's going to go high, right? Make sense? I could also look at like chip select, or I could look at write if I'm looking for a write. So I'm going to set my trigger on the rising edge, and then I'm going to go into the software and I'm going to have it read. When it reads in the software, it'll trigger SignalTap and it'll show me from the hardware perspective what's going on. So this will end up giving you a waveform much like you would see in ModelSim, except it's being read from the actual hardware instead of from a simulator. So this can allow you to debug the hardware, and you can have it running with your actual software at the same time. I don't know if I don't even know if the simulation model for the Neos even allows you to do that. Like, I don't think you can run software on Neos. Now, the main downside of this is, of course, like I said, every time you add a new signal, you have to compile. So you should add as many signals as you can initially, so you don't have to go back and add signals later. Of course, in our case, there's not that many signals to add. We added them all the ones in our component. All right, we're almost there. Fitter's done. Timing analysis done. All right. Okay, we're good. So we'll go back into signal tap. I'm going to hit this button to program the FPGA. You can program it through any way that we want to program it, but there's a program button here. So I've programmed it. Now I can hit the capture button. Now, right now, I don't have any triggers set. All the triggers are don't cares. So it's just going to capture, you know, it's just as fast as it can. So now I've got, you can see that, interestingly, I'm actually kind of surprised that you can see data being written there. But this data is not intended for me, not for my peripheral, because oh, tell me I added write and read. Oh, no, I didn't, did I? Oh yeah, slave read. Okay, I do have it, yeah. So slave read is just flat because I'm not reading it. I actually didn't put slave write, but that's fine. And chip select, of course, the chip select is the main thing. That's 0, so. Okay, so I'm gonna stop capturing here and I'm gonna go back to the setup tab and I'm gonna say slave read. I'm gonna change this to rising edge and I'm gonna hit capture again. And now it's just gonna say acquisition in progress. No, nothing's happening. So if I go back to my software and I type Neos 2 GDB server port 5000 TCP persist. TCP port. There we go. And I type Neos elf GDB lights.elf and target remote localhost 5000 and load. Okay, here we go. So now I'm ready to go. I'm connected to the debugger. So all I have to do to read from the Neos is I have to print, I can dereference address 0, right? So I can print the contents of address 0 because address 0 was the base address. Actually, I don't even have to use 0. I can put 4 here, or I can put 8. Let's say I read from address 8. That's going to be a word address of 2, right? 8 divided by 4, okay? So now if I go back to signal tap, it's waiting for acquisition and POW. So I read that value and it should have triggered, and there it is, triggered. So if I zoom in, you can see the chip select and slave read both went high, and the read data should say 2, because I put 8, and 8 divided by 4 is 2, right? But if I zoom in, I'm sorry, not the address is, sorry, not the data. The address is 2, right? So I'm reading from address 2, and the value I read was, there's my data that I read, CBB2ED57F, right? That should be the count value, right? What's the count value? Do I have the count? Yeah, check it out. There's the count value. And not only that, but you can see the count value also reset to 0 as it was supposed to, right? So the count value was sent back to the host and it was then reset at 0. Now the question is that what I actually read? Well, that, I need to, dang it, hold on. One more second. Wait, hold on. Let me hit go again. Or it's already, sorry, it's automatically going to go. I should have put /x here to read in hexadecimal. Okay, so if I do that again, let me put 12 here too, just for the heck of it. Okay, so now I just read again. And address is 3, 12 divided by 4 is 3. The count was F7373044. That was also what was there. And if I go back to GDB, that also matches what GDB read, right? So it works. Now, if there's a bug in there, you would be able to debug it doing this kind of testing. Now, unfortunately, I ran out of time. I wanted to write some software that did 2 consecutive reads, but I'll just give you a spoiler. I did this in my office, and it took, I wrote a loop, actually not even a loop. In my Neos code, I had read in 2 lines of code. And then I looked at signal tap, and I also looked at the result, and it was 7 cycles that I got. And so it took 2 consecutive reads from the software were separated by 7 cycles. So if I were trying to do bulk data transfer, it would take about 7 cycles for every 4 bytes of data that I read from the Avalon, which is pretty abysmally slow if I'm trying to do high-speed copying, right? So I didn't get to, but you can try that if you want. Okay, so I think you guys have everything you need for lab 3. And like I said, I'll extend the due date 1 week, whatever 1 week from October 27th is. Okay? We don't have a quiz this week either. So we'll see you in lab on Thursday.